So the first paper is super interesting. I think all the papers in this session are super interesting because I like networks and AI. Chen Zhu is from Peking University and is a first-year PhD student, advised by Professor Gui Liu. And you'll hear all about his work in 2 seconds. But this is quite an interesting take. And if you think about this while you're hearing the talk, if you have any questions, then be prepared to put your hand up. So over to you.
Good morning, everyone. I'm Chen Zhu from Peking University. I'm honored to be the first presenter today. Today, I will introduce our latest work, InfiniteHBD, and show you how to build a near-ideal high-bandwidth domain. This is a joint work with Stefan and Light Legends. Let's start with a typical story. As technology advances, models keep getting larger and larger, from XNet to GPT-3 and GPT-4. Training compute is rapidly scaling. However, a single GPU is no longer enough for LLM training. Scaling LLM training now relies on parallelism strategies. These strategies split model and data across GPUs in different ways and use collective communication to stay in sync. We divide them into 2 groups based on their communication volume. Data parallelism and pipeline parallelism are communication low. Tensor parallelism and expert parallelism are communication intensive, often an order of magnitude higher. So, how does Datacenter support LLM training with these 2 groups? The traditional data center network, or DCN for short, uses InfiniBand or Ethernet with factory or real optimized topologies. They provide 200 to 800 Gbps bandwidth, which works well with communication low parallelism like DP and PP. However, DCN could not support communication-intensive parallelism like TP and EP efficiently. TP and EP requires TPPS level bandwidth, which only high-bandwidth domain can provide. That's why high-bandwidth domain, or HBD for short, is essential for LLM training. Now that we know why HBD is so important, our talk will be organized into 3 parts. Let's start with the first part, existing HBD architectures and their limitations. We group existing HBD architectures into 3 categories based on how they connect GPUs: switch-centric, GPU-centric, and switch-GPU hybrid. But all of them suffer from scalability, cost, fragmentation, and fault resilience issues. Let's go through them one by one. The first type is switch-centric HBD. They connect GPUs using high-performance switches to form a non-blocking network. A typical example is NVIDIA GB200 NVL series. On the left is NVL36. The strength of this architecture is a high-performance NA-to-NA communication. However, it comes with clear drawbacks. First, the heavy use of high-performance switches and links, like NVSwitch or NVLinks, makes it very expensive and limits its scalability. Second, the limited scalability leads to significant resource fragmentation. For instance, in NVL36 with TP16, one node always remains unusable, even when it is healthy. Finally, the failure of single switch will degrade the bandwidth of all connected GPUs. We call this switch-level fault explosion radius. The second type is GPU-centric HBD. They use direct GPU-to-GPU connection to form a mesh or torus-like topologies. Examples include SIP ring and Tesla Dojo. On the left is the SIP ring. They reduce the use of switches and links, which lowers cost and improves the scalability. However, the drawbacks are significant. First, the collective communication they can support efficiently is limited, and the NA-to-NA communication is low. Second, they suffer from HBD level fault explosion radius. If one node fails, its link goes down. This degrades the bandwidth of its neighbors and breaks the entire topology from ring to line, degrading the whole HBD. Tesla Dojo is similar. The failure of one node degrades its neighbors, break the whole topology, and degrading the HBD. The third type is switch GPU-centric, switch GPU hybrid HBD. They combine direct GPU to GPU connections with switch links. A typical example is Google TPU v4. As shown in the figure, TPUs are connected directly within 4x4x4 cube, and the cubes are linked through optical circuit switches, or OCS for short. The strength of this architecture is a moderate cost, scalability, and any-to-any performance. However, the drawbacks are twofold. First, it still suffers from switch-level fault explosion radios. The failure of the single OCS will degrade the all-connected cubes. Second, the cube-level fault explosion radios. The failure of single node inside one cube breaks the cube topology, degrading or even disabling the whole cube. To summarize, all these architectures suffer from serious drawbacks. None of them can fully meet the demanding of LLM training. So, what are the key attributes of an ideal HBD architecture? We have 3 observations. First, the large and adaptable TP size is critical. As shown in the table, high modal flops utilization, or MFU for short, requires large TP size, which means HBD should offer low cost and high scalability. Second, HBD requires high resource utilization and fault resilience. In practice, clusters are maintained at the node level, so the node level fault isolation is ideal. Third, under these constraints, it's hard for HBD to support all collective communications perfectly. But here is the key. MOE can also be trained efficiently with TP instead of EP. As shown in the table, TP training avoids EP imbalance problem, achieve equal or even better MFU than EP. This means that HBD needs to only support TP reduce efficiently, which greatly simplifies the design and make an ideal HBD possible. We just summarized the key attributes of an ideal HBD, but how can we achieve them? Next, we'll introduce our solution, InfiniteHBD. Our key idea is to build a transceiver-centric HBD. We unify connectivity and switching at the transceiver level using optical circuit switching, or OCS for short. Our solution has 3 parts: the OCS transceiver hardware, the rectangular K-hopping topology, and the HBD descent orchestration algorithm. Because of time, we'll only focus on the first of 2. You can find the orchestration algorithm in our paper detailedly. The first design is the OCS transceiver. We integrate OCS into standard QSFP-DD 800 Gbps transceiver. The OCS is based on silicon photonic and light switch metric, which is simple, cheap, and energy efficient. For functionality, the OCS transceiver connects to 2 GPUs inside one node and provides 3 communication paths. 2 external paths connect to other nodes, and 1 loopback path connects to 2 GPUs locally. These 3 paths are time division multiplexed, with only 1 active at a time. The reconfiguration latency between them is 60 to 80 microseconds. The OCS transceiver provides strong functionality and efficiency, giving us the opportunity to build a near-ideal high-bandwidth domain. The second design is the rectangular K-hopping topology. In the topology, each node connects to all other nodes in the cluster within K-hops via OCS transceiver. On the right is the 2-hopping topology. For instance, node 4 connects to node 2, 3, 5, and 6 within 2 hops. On the left is the detailed view of node 1, 2, and 3. The red lines denotes the intra-node connections, and the blue lines denotes the inter-node connections. The first feature of the rectangular K-hopping topology is the dynamic ring construction. By activating different paths of the OCI transceiver, we can build a GPU granular ring of upstream side and upstream location. For instance, node 1 and 2 can form an 8 GPU ring. Node 1, 2, and 3 can form a 12 GPU ring in a similar way. The second feature is the inter-node fault isolation. By bypassing the faulty node, we can achieve nearly no-level fault exposure radius, which is nearly ideal. For instance, when all nodes are healthy, we can deploy multiple TP groups in the cluster. But when node 2 fails, TP group 1 becomes unavailable. At that point, you can simply bypass the node 2. Activate the link from node 1 to its next nearest neighbor, node 3. Node 1 and node 3 can form a new TP group. In this way, we can isolate the failure of node 2 within the node without affecting the rest of the cluster. These designs bring us very close to a near-ideal HBD. The simple K-ring topology and the cheap OCI transceiver gives InfiniteHBD low cost, high scalability, and few fragmentation. The inter-node fault isolation achieves near node level fault exposure radius, which is nearly ideal. The dynamic ring construction enables InfiniteHBD to support dynamic TP ring modules efficiently. Now, we will show our evaluation results. Our evaluation has 3 parts: the evaluation of the OCI transceiver hardware, the fault resilience simulation, and the estimates of the cost and power. Our simulation based on 348 days fault trace collected from a production 3000 GPU pre-training cluster. The fault trace includes the fault pipes and distribution, which is open sourced on GitHub. To compare, we use these baselines: the Big Switch ideal model, NVIDIA NVL series, Google TPOV4, and SIP ring. Firstly, the OCI transceiver hardware evaluation. We separate the OCI transceiver into 2 parts: the core module, which provides OCI's functionality, and the peripheral circuit. Measurements show that insertion loss of the core module is 3.3 dB at room temperature. Moreover, the power consumption of the power module is 3.2 watts. Together with the 8.5 watts peripheral circuit, the total power consumption is stay within QSPDD 800 Gbps specification. Finally, the bit error rate is close to 0, showing its reliability. Next, the fault resilience simulation. Using the fault trees, we measure the ratio of weighted GPU over time under different HBD architectures. The measurements show that the InfiniteHBD is close to Big Switch ideal model. Moreover, compared to TPOV4, it reduced the weighted GPU by 14 times, and compared to NVL72, it reduced the weighted GPU by 20 times. This shows the strong fault resilience. Finally, the estimates of the cost and power. We normalize the cost and power by the bandwidth per GPU, so they can directly comparable. In terms of cost, InfiniteHBD achieved the most cost efficient. It is 3.2 times cheaper than NVL72 and 1.5 times cheaper than TPOV4. In the terms of power, InfiniteHBD is also the most efficient. The power consumption of InfiniteHBD is 1.3 times lower than NVL72. To wrap up, let me briefly summarize. Training LLM requires HBD. However, existing HBD architectures suffer from many issues. To solve this problem, we propose our solution, InfiniteHBD, a transceiver-centric HBD. Our solution has 3 parts: the OCI transceiver hardware, the recombinant K-ring topology, and the HBD design orchestration algorithm. The evaluation results show that the OCI transceiver has a low insertion loss, low power consumption, and low bit error rates. Furthermore, InfiniteHBD achieves high fault resilience, high cost efficient, and high energy efficient. Overall, we build a near-ideal HBD in InfiniteHBD. That's the end of my presentation. Thank you for your attention. I'm happy to answer any questions.